Welcome to the Crazy Hat Chemist. So another video here on Thermochemistry Part 2. So let's get moving. Bam! So today we are talking about entropy or delta S. A very complicated subject, and as you get further in chemistry into your master's program, you're really going to understand entropy much better than you are now. But I'm going to give you a little bit of information here to get you started on what entropy is all about. So, the measurement of the randomness or disorder of a system, that is entropy. The unavailability of a system's thermal energy, that is entropy. The fundamental driving force for the majority of reactions, a spontaneous process, is always associated with an increase in entropy of the universe. That is the second law of thermodynamics. Entropy can be associated with probability in statistics. So that's why you're going to take that statistics course and understand that there is truly an application for this course that I'm taking. Okay, here is a deck of cards. An ordered state is low probability. An example is a brand new deck of cards where all the cards are organized in suit in sequential order. This is a low probability, or it takes energy and is low in entropy and thus a negative value. That is, delta S is less than 0 and is, of course, reactant favored, just like that deck of cards that I had out there. A disordered state has high probability. An example is the game, quote, 52 card pickup. I remember my friend Tim from grade school a long time ago, and he said, "Hey, Phil, do you want to play a game?" I'm like, "Yeah, let's play a game." He said, "Let's play 52 card pickup." And I'm like, "Okay." And then he just took the cards and tossed them. And I didn't understand what 52 card pickup was until Tim introduced me to that wonderful game. Thank you, Tim. So 52 card pickup is where the deck of cards is tossed, and then thus all the cards are unorganized or disorganized. This is a high probability event and occurs spontaneously in chemical reactions, that is, and is a high entropy and thus has a positive delta S. So delta S is greater than 0 and of course is product favored. And here are all those cards spread throughout, just tossed. UC Davis, my alma mater. Okay, here is glass that has been broken. So the glass is very organized, and then boom, you crack the glass, and then that is a very high disordered state. Humpty Dumpty, when Humpty Dumpty fell off the Great Wall, that is a great disordered state, because all the king's horses and all the king's men couldn't put Humpty Dumpty back together again. Just like that glass that was broken, it's very difficult. It requires energy to put it back into an ordered state. With that egg, that's going to be impossible for that to do. Okay, in order to understand entropy, let's look at state changes with water. Okay, when water is in the solid state, as in ice, each internal water molecule is hydrogen bonded to 4 other water molecules, maximizing the number of hydrogen bonds possible. Consequently, this forms a crystalline hexagonal structure. It is regular and repeating and thus highly organized. Each water molecule can vibrate but is fixed in position and cannot exchange positions with other water molecules. In this state, the solid state, water has a low probability of having different locations and therefore the entropy is very low. As ice is warmed past the melting point, water is converted to the liquid state. In the liquid state, the internal water molecules at any given moment has between 2 and 3 hydrogen bonds with adjacent water molecules. Since water is in the liquid state, the water molecules are moving, i.e. they are not stationary as in the fixed solid crystalline hexagonal structure of ice. And the water molecules are exchanging positions with other water molecules, thus breaking and forming hydrogen bonds constantly, depending on the temperature. Therefore, each individual water molecule can rotate, flip, and change positions with other water molecules. Yet water is still confined by the container, as all liquids are. In the liquid state, water has an increased number of possible positions and locations as compared to ice, and therefore water in the liquid state has a higher entropy than ice does. All liquids have higher entropy than their solids of that same compound or element. As liquid water is heated past the boiling point, water is converted to the gaseous state, of which water molecules are now individual and separated from other water molecules, i.e. there are no hydrogen bonds with other water molecules. This means that the gaseous water has no hydrogen bonds with other water molecules. Furthermore, gaseous water is moving faster due to the increased temperature. Kinetic energy is proportional to temperature, and the water molecules have additional rotational energy, spinning of the molecule around its axis, vibrational energy, movement of atoms within a bond, and translational energy, movement of the molecule through space. The number of possible potential positions and locations of which gaseous water can be is an enormous number, considering that gases fill their container, or if they're not in a container, then they keep on expanding. Therefore, gaseous water has the highest amount of entropy of any state of matter with regards to water, as all gases do have a higher amount of energy, higher entropy than their liquid and solid counterparts. So here's a diagrammatic view of this. I have solids, liquids, and gases. Solids relatively have low entropy and low entropy delta S. Okay, you should see that that solid with all the yellow dots there are highly organized. Liquids, they are moving and exchanging positions. Gases have highest entropy of all the three states because those gas molecules are expanding. They are not touching one another, unlike in the liquids or solids. Okay? So, another example of entropy with water and salt, just to give you another example. Imagine a beaker of water molecules in the liquid state. The molecules are relatively organized with between 2 and 3 hydrogen bonds for each internal water molecule. Since it is pure water, then the entropy is relatively low because the organization of the liquid structure itself and the vast number of hydrogen bonds. Now consider a salt, sodium chloride, of which is an ionic solid. Okay? The salt is highly organized with alternating cations, sodium ions, and anions, chloride ions, in a regular repeating crystalline structure. This has also relatively low energy. Okay? Then examine the addition of the salt, sodium chloride, to the beaker of water. There are two processes involved in this. Number one, the mixing of the solute, that is the sodium chloride, with the solvent water, assuming that the salt is less amount than the water. That's why it's the solute. Number two, the dissociation of the compound sodium chloride into its ions, that is the sodium ion, cation, and the chloride ion, the anion. Both processes lead to an increase in entropy. However, there is one process, the energy of hydration, which causes water molecules to become ordered around the ions themselves and leads to a decrease in entropy. That is counter to steps 1 and 2 here that I aforementioned. Overall, for sodium chloride, there is an increase in entropy with the addition of sodium chloride to water. So it's overall a very highly entropic reaction. Make a prediction about the following the entropy in the following circumstances. Number one, molecular bromine, that's Br2, is one of two elements that is a liquid at room temperature and pressure, mercury being the other. If a beaker of bromine is left on the bench top, the bromine will evaporate. That's because it has a low boiling point. So what do you think will happen with the entropy as bromine evaporates? Here's our answer. Bromine is undergoing a state change from a liquid to a gas. This is an increase in entropy. That is, the delta S is positive. That's greater than 0, since there are more possible positions of the gaseous bromine than the liquid bromine. Gotcha. Number 2 example, if a 1 centimeter by 1 centimeter cube of glucose is added to water. Think about this. The glucose in a crystalline structure is added to water. Both the glucose and the water are highly organized to begin with. Okay? Now, the glucose, okay, is a non-ionic solid, i.e. it's a molecule, and will dissolve and not dissociate in the water. It will disrupt the regular array of the water's structure and hydrogen bonds, causing the dispersal of matter with an increase in the entropy. That is a delta S, which is a positive value. Okay, number 3. 2 different containers at the same temperature and pressure. One container has nitrogen dioxide, the other container has dinitrogen tetroxide. We use this example to calculate the change in entropy of this reaction already before in a previous video in this unit here. So these two, what's very important about this is that they're at the same temperature and the same pressure. Okay, and then we need to look at NO2 and N2O4. Since the conditions of temperature and pressure are the same, the molecular complexity needs to be analyzed. NO2 has a lower molar mass, it's less complex, and is less complex than N2O4, which has a higher molar mass and is more complex. Therefore, N2O4 has greater entropy than NO2. Okay. Number 4, the cooling of molecular oxygen from 67 degrees Celsius to 22 degrees Celsius. So even though there is no state change in this, right, molecular oxygen is still a gas, the oxygen cools and the number of possible positions have decreased, leading to a decrease in the entropy. So entropy is negative. As the temperature decreases, the rotational, vibrational, and translational energies all decrease. This is a decrease in entropy. That is decreasing, that is delta S is less than 0. Number 5, the condensation of water on a mirror. So we have gaseous water condensing on that cool mirror. So the state change from a gas to a liquid is a decrease in entropy. That is a delta S is less than 0. The number of possible positions has decreased. Okay. The entropy of the universe is the sum of the entropy of the system and the entropy of the surroundings. So hopefully I've given you a number of examples. Now what we're going to do is we're going to come up with a mathematical equation that we aforementioned in the original video of this series. And here is that equation. The delta S of the universe is the sum of the delta S of the system plus the delta S of the surroundings. So this is delta S of the universe is the entropy of the universe. The delta S of the system is the entropy of the system. The delta S of this, and this is the dispersal of matter is the delta S of the system. The delta S of the surroundings is the entropy of the surroundings, and this is the dispersal of energy. That's a very important equation. Remember, the entropy of the universe is always going to be a positive value for product-favored or spontaneous reactions. The second law of thermodynamics states that the entropy of the universe is always increasing in a spontaneous process and is therefore positive. So that delta S of universe is going to be positive almost all the time. That is this great positive value. Whereas there is no change in the entropy of the universe of a system at equilibrium. The sum is therefore 0. So I'm going to replace that greater than 0 with an equal to 0. Okay? Entropy. I love entropy. The universe is always going towards more entropy. You gotta love entropy too. I am the Crazy Hat Chemist, and I actually do have a crazy hat for you this time. Oh, you gotta love this hat? This is a crazy hat. If you like my videos, give it a thumbs up. If you love my videos, subscribe to my channel and please pass them on to all your cool chemistry friends. And if you like my videos and you want to see more, then please donate to my website. You might be able to get yourself a sticker or maybe even a super cool t-shirt with that super cool back. I love that t-shirt. There's my symbol. You got to get one of these for your hydro flask. Everybody needs one of these. I hope you have a great day, and I will see you next time for more cool chemistry videos. Bye for now.